Hello guys, welcome back. So this is video 2 of our series on PANDA challenge from kaggle. So today I just thought we'll go over the initial EDA I have done so far, where we'll be talking a lot about what the data set is, what it is containing, and how we could capitalize what is provided to us, and what should be the next step towards making our deep neural network model, and you know try to tackle this problem. So I'll just go over and I will explain this. So I have already made the kernel. So this video will be short in length, because if I sit here and type, it will be a long video. So this way it is better. So I will give the link for this EDA also, and there are a lot of really good kernels that are released in the Kaggle page for this competition. So I would encourage everyone to check it out. There are a lot of things you could learn from them. So I'll just start by going over it. So I always prefer to keep this one, which this particular cell, which is provided by the kaggle kernel itself whenever you spin up a new kernel, because like it just helps you with getting the path for whatever you need, because I'm not that good with remembering paths, so I always prefer something like this to help with me. So I'll just for this initial analysis, we don't need any GPU TPU, so I'm just going to go with none, and I will keep internet on, because if I want to install some packages, having this internet on will be a good thing. So yeah, I'll just refresh this. This happens sometime when you change the hardware of this kernel, but I don't know why this time we didn't even change it, but okay, it's fine. Yeah, okay, I'll just go over it. So here, this data section, you can see what data is added. So I'll just, if you don't know, the easiest way is to run a notebook, spin off a notebook with this data set provided by the competition. Is just go to notebook and then click a new notebook. This will spin up a new notebook for you, notebook instance for you, with the data set already added to you. So you don't need to download this 193 GB data, which is hard. So if you want, you can just use this API that is given here. You have to install Kaggle API, and then you have to get your Kaggle token, which you can find it in your profile, and then you can download it. So in our case, we have this pandas data. So train image, train label mask, sample submission, test and train CSV. So all these things are given to us. We can simply access them by if you want to call them, if you want to import any images, load any images, you can simply call them through this path for this. So kaggle /input/ prostate cancer grade assessment, and then followed by the file name, whichever you want to call. So it's that simple. So quickly I'll go over it. I need pandas for reading the CSV file, and matplotlib for plotting all the images, numpy array, skimage.io. Since we are using having TIFF data, this is required. And there is also another another package which we will be using to read images from this TIFF format. I will talk about it more when we go through that. So OS, and then I want TQDM just for some visualization, and random package. So firstly, I will just start with reading the test CSV, and then visualizing what it is having in this train CSV. Sorry. So it has 4 columns. One is image ID, which should be the ID of the image, and then data provider correspondingly the source. So in our previous video, we saw there are two data providers. So those institute names are given here. And then is upgrade, this is your final target which you need to figure out. And then grades on score, this is how the target is calculated. You can use this as an intermediate step, your model predicting grades on score, and then followed it with is up score grade prediction, or you can directly predict it. It's up to you. So they have provided both the data for you, so you can find a best possible combination and you can use it. So we'll just start by looking at some of the images and what does the image contain. So I'm just reading a random image from here. I'll just to visualize how it looks. So this is how the sample looks actually. So this is a sample of the tissue, I guess, which is going to contain the cancer or some information about it. Yeah, so we have to process this one. So just by looking at it, we can see the image is having a lot of white spaces. We need to get rid of it, and the image is quite big actually, more than 1200 plus resolution, cross 2000 plus resolution. So we can't just literally pass this image into a neural network, because the network will be really huge because of this input dimension. We have to do some method to remove all these white spaces. So yeah, so we'll keep that in our mind. So next thing, I will just go ahead and print some more metrics on understanding this one better. So it looks like there are around I'm just printing the number of image ID which are unique. So it's nothing but counting how many unique rows we have in this train data frame, and we have around 10,616, which means we have around 10,616 images. So which is what we are seeing here. So I'm just printing the length of how many total number of files that are physical files that are present in the inside image train image. So this is the directory which is containing all the train samples. So it is totaling around 10616, which is same as the number of training rows. But here they have also provided a training label mask, which is not the same number, which is 10516, which means we are short by 100 masks. So there is 100 masks which is missing from this dataset, or 100 masks which is not provided to us along with the images, which means there are only 10516 pairs of images and masks available, so which we need to tackle. So here what I thought is like I will just go ahead and remove all the missing samples and keep only the samples which are both the image and mask pair, because I don't want to I want to work with a model which takes both the inputs and gives me some prediction out of it. So for that, if I would like to train this model, then I need both the input and mask pair. So I will just go ahead and remove all those images which is not having mask. So I'm just going to do the same thing, make a list of all the files that are present in the train label mask, and then I'm just going to strip out all the unwanted things and only keep the ID of it, so the image ID. So the file name is like, I'll just go to the corresponding one. So if you see inside this train label mask, the file name is like the image ID followed by underscore mask.tif. So this is not required for me to compare, so I only need the image ID to work with. So I'm just going to split the string using this underscore, and then I'm going to take the first one. First one is nothing but the image ID part. So here you can see, so this is the image ID which we got out of it. So I'm just going to go ahead and this is a list of all the image ID which are present in the mask, and then I'm going to go ahead and make a new data frame. I'm going to call it as mask data frame. So what I'm going to do is, like, I'll just take this new data frame and then compare it with the old train data frame, not old but train data frame. I'll just drop the rows which are not present in both the data frames. It's simple as that. So I'll just do that. I'll just create a new one. So this is how the new one looks like. Just row count and then a column image ID, which will have the image ID. So here I'm just going to use panda's merge function, which will merge two data frames, and I'll just give the column name as image ID. So wherever the image ID entries in the columns match, both the data sets will be merged. So this will just remove all the unwanted data from it. Okay, so this is another issue with kaggle actually. So this is sometimes annoying also, but fine. Yeah. So here you can see it has done, and then this train df correct. It has around 10516, which is the total number of masks available. So yeah, so we have done the thing. So this is how it looks like. So image. So no changes. We just deleted some rows of images which is not having mask. So simple as that. So next thing we have to do some more processing on the image side and see how it looks like. So I'll just explain these things once we get to this part. I'll just start with taking you over this display function. So I just thought I want to display both the image and mask together and see how they look, and what we can infer out of it. So I'll just go over this display image mask function which I made. So this display image mask function takes in a data frame and then choice. So choice, I just want to be like whether I should give a number or an indices which particular sample that needs to be pulled up and displayed to me, or just pull a random image and show it to me. So yeah, so that's what is happening here. So I'm just going to whenever someone it will just generate a random integer which will be acting as the index value to be retrieved, the row value to be retrieved. So image ID and then source and then is upgrade score. So these things will be pulled off from the data frame for the randomly chosen image ID. And then the path is nothing but this is the initial extension till the file directory, and then followed by the ID of the image, and then TIFF, and then mask. Those information which we need to that's the location of the file. And then I'm going to use skimage.io multi-image function to read the TIFF file. So I'm just going to pass the image path and then the mask path, and then retrieve image and then mask. So here comes the interesting part actually. So we have seen in our past sample, when we try to visualize, we saw there is a lot of white spaces, right? So I just need to crop off the white spaces and only show the places where the content is there. So for that I just made a function image crop, which will take both the image and the mask, and then it will crop it for us. So there should be a logic behind how to crop it. So it can't be like just some fixed boundaries which you can crop out, because like each image is different from one another, so there's no fixed bounding box or anything which you can follow. So it should be like dynamically finding it. So one way to do that is we know both the mask provided. This one, when we read the data description, we came to know from both the sources the background are kept as 0. So the value in the mask will be, for background it will be 0. So in both the cases, so we know like wherever there's 0 there is no content, right? So I'm just going to use a numpy function, a non-zero, where it will just return, and then going to pass in the mask, and then this will return to me the indices of places where there are non-zero values. See, like values apart from 0, so 1 and 2 or 1 through 5, wherever these numbers comes in, you'll get the indices for that. So I'll just take the extremes of this non-zero indices which we got. That should be giving me the extreme ends of the bounding box inside which we can find the colored images. So non-zero 0, 0 will be for the y channel, for the y, and then 1 will be for the x. So like for 0 for the first dimension, and then 1 for the second dimension, and then 2 for the third dimension. Since we need everything in the channel side to be given back to us, I'm just going to put all for it. For this 0 and 1, 0th channel and then 0th dimension, first dimension, I'll just do the min and max. So minimum value and maximum value, same thing, min value, max value. The same thing I will follow for both the mask and then the image passed in, and then I will just return those things. So this will be a cropped image. So image and mask scan will be the cropped image of the initial image which we read. And for visualizing the mask, so mask is having some kind of encoding which is being followed by both these institutes, right? So we need a way to visualize cancerous cell, non-cancerous cell, and background, so that we could actually see which places they are marking and what is the meaning that is being carried out on that. So for that I made another function which will just take the image mask and then the source meaning source of it. So source will be where it is coming from, and then is I will just pass the score also. But right now I'm not using anything, I'm not doing anything productive with the score, but that I just did for future analysis. So based on the source, if the source is from this particular institute, then we'll do certain kind of encoding, decoding, and then if it is from another institute, then we'll follow some other method. So from this institute, we have come to know from the description, like if it is a 0, then it is a background, like it has no tissue, and then 1, then it has some tissue, mainly stroma and epithelium combination, and then when it is marked as 2, we have cancerous tissue. So they have only encoded all these information in the red channel, and the green and blue channel are just empty zeros. So we can't get any useful information from it. So that's what I'm doing here. So 0 is the red channel, and then if it is equals to 1, then I will just set the final image, final mask which I will be returning, channel 1 to 255, and then channel 0, if it is equal to 2, then I will set it to 255. So the simple meaning here is red for cancerous tissue, and then green for green for healthy tissue. Okay, so the same thing I will follow for this another institute also, red band institute, where 0 means background, so we don't need to worry about background, so I'm not doing anything with that, I'm just throwing it away. And then 1 and 2 means healthy tissues, or not interesting cancer tissue. and 3 to 5 they are cancerous tissue. And this institute, they are also labeling based on what type of score, Gleason score, that particular region is 3, 4, and 5. So this, we could use it also in our future analysis. But right now I'm just encoding all these cancerous tissue as red, and then others as green. So I'm not doing any separate encoding for each cancerous tissues availability. So this will be returning a new image, mask image for us. So new mask image, and then I'm just going to print some more details, and then I'm going to show it. So I'll just go ahead and run this one. I'll just show, I'll just quickly show everything. So I need to run these things also. So the informations are printed are like the image ID. If you need to, like, if you find something weird in this or something interesting in this particular image, you can quickly grab this image ID and do further analysis on it. And then image shape, mask shape, source, the score of it, and then this one you can just forget it. So this is from the Karolinska Institute, and this is how they are doing their mask. So it looks like this entire region is marked red, which means some type of cancerous tissue is present in this place, and then this green represent this is a healthy tissue as far as we know. And there are like missing part also, which we need to consider, like take it into consideration when we are doing further analysis on it. So I'll just do few more passes, and we'll see if we can find any interesting things. So this is another place where all the places are marked in red, which means cancerous tissue, and then it is from the same institute, Karolinska. Karolinska. Okay. And then the same institute, I'll just hope to find yeah, a red bond. So here you can see no, we saw several examples of the previous another institute. This institute, their marking is more finer, it looks like. Individually, cell wise, their location wise, they are marking. We don't know whether it's good or bad compared to the other source, but this is quite interesting also. So this is how the mask from the other institute is looking like. So moving on, yeah. So I'll just talk briefly about this. So with this data set, I just found some issue in this data set where there are few instance of mask which is having no information at all. And then before going into how I find it, but I'll just talk about I found it accidentally while I was doing some other analysis. So I wanted to know what is the overall distribution of height and width of this images, so that I could use it for coming up with the best resize shape, which will be not losing much more, not losing any lot of information. So I just wanted to do some run on that and then store the width and height. But it turns out like while doing that, I came across some instance where it was not returning any non-zero values, because there was no non-zero values at all in the mask. So like mask should contain some non-zero values, but there were no non-zero values, which means the masks are like not good, like the mask is not at all containing values, which is a kind of a small problem in the data set. So yeah, I just found that, and I'll just explain how I did that. So I'm just going over the rows. I'm just iterating over the rows in the data frame, and I'm just going to read the mask of it, and then I'm just going to read the mask and then I'm going to pass it through the image crop. I'm just going to get the cropped image, and this I'm going to find the shape of it, and then I'm just going to find the shape of it, and then I'm going to store it in the data frame. But right now I'm not doing the data frame storing thing. Since I found another interesting thing, I just wanted to find what are the details regarding that interesting parts. So I'll just run it. It will take a while. So I'll just go ahead and run this one. Yeah. So if you find some error like that, and if you don't find any error in your code, just run it again, because that is some small bug with the notebook. So I'll just cut this video to where I have this run finished, because it will take quite a while, because we have to go over 10,000 samples, right? So yeah, I'll meet you once it is done. Okay, it's done. Okay, so it took around nearly 12 minutes to run. Maybe I'm not doing anything better, or is it with the skimage.io that is not doing a fast reading of this diff file? There are a lot of things which we could analyze, but this is like for reading 10,516 sample and doing a small cropping function. It took us around 12 minutes, which is a lot. So yeah, so these are the four samples, luckily just four samples where we are not having any non-zero value. So I'm printing the what am I printing? So yeah, here I'm printing non-zero. So non-zero is like np non-zero. So this should return some values, but in our case it is not returning anything. So here it just returns an empty array, which means there is nothing, no non-zero values present. So these are the index of those images, which is very important, so that we could go ahead and do some understanding on it. So here what I'm doing is I'm just going to copy one such example of it. I'm just trying to visualize it. For some reason this is not working. Yeah, okay. So here, non-zero, we don't have anything non-zero, which means nothing is there. So moving on. So yeah, those just look out for these images. You need to remove them when you are when you're going to train your neural network. So yeah, so moving on. So I'll just print some metrics on it. So this is like data provider. We have only two. Surprisingly, we don't have any some random or a new institute that is popping up. So we just have only two of it, and then we have a total six values to predict. So 0 through 5. So six unique is upgrade count is upgrade values are there. So count wise, we have, this is a breakdown of number of samples that are available for each grading. So 0 we have around 2.8k, whereas for 5 we have only 1.2k available to us. So, and that's something which we can do. So yeah, we have a class imbalance problem here. So how are we going to address it? That could be a key in the challenge. Yeah. And then this is the breakdown of data providers. This looks like this particular institute has around 400 samples, higher than this red bond. So which means your model might be preferring to learn or preferring to go with this particular data provider compared to this. So you have to do some kind of work there to make it work on both the things, because we don't know, this is like the train distribution. We don't know how the data is in the test side of it. So you can't just have something leaning towards one data provider, and what if the data set is like equal, which has both data providers equally or one data provider dominating in the test data set. So that's something which you need to look for it also, keep in your mind. And I was talking about another way to read it. So the importance of this particular method is like what we have is called as WSI or yeah, got it, whole slide image. So this is something in the biopsy field. What they will do is like they will take a scan, they will take a segment of a tissue and then they will add some color to it, and then they will be inspecting it, right? Let me just pull up a correct source for it. This whole slide image in this pathology, yeah, we'll just stick with those terminologies. Then in the pathology department, so what they will do is they will take a sample and then they will add some color to it, and then they will do study on it. So what is this whole slide image is like, they're going to they're going to convert it into a digital representation, uh, which they could like previously they would use some, I guess they would use some microscope to look into those patches, but if they want to digitalize this, they will be following this whole slide image method of it. The reason is like it should be in higher resolution. So here you can see the whole image, and then they are actually inspecting a small patch out of it for detecting about the knowing more about this disease or cancer in our case. So they need a higher resolution image to be able to capture all this information. So when they zoom in, they will not lose information. So when you zoom in a digital picture, you will end up with pixelating the image, which is like not carrying much information which you could understand it, right? So they want to avoid all those things. So that's the scenario, what's the idea behind it. So the stiff files are whole slide images of individual tissues, and this open slide is a Python package. Is a package, not a Python package. It's a package which will be helping us a lot with reading all these things. So I would suggest everyone to go through this at least once, like to understand what are the informations carried and how to retrieve once you load the TIFF file using this open slide package. It will be really helpful. So basically it has like uh, multiple levels of resolutions and more information added in that. So yeah, so and the output will be in RGBA format, not just RGB. So yeah, so I'll just go through what I have done so far. So I'm just going to import this open slide. Yeah. And then I'm going to read another random sample just for our investigation. So I'm just going to put this object in this image image variable. I'm just going to see what this image variable contains. Currently it should contain more information, but yeah, so just ignore this part. Okay, so image dot property, so this gives us information about the property of this file. So here we can see a lot of interesting things. So here we can see open slide level count, which means how many different resolutions are given in this particular thing. So here they have 3 resolutions. So level 0, level 1, and then level 2. So 3 different levels they are telling. So this is the downsample ratio. Here there is no downsample, and then this is the height. So 18,000 uh, height, and then width is here around 8,000. So this is without any downsampling, and then here they are doing a downsampling of 4, which is nothing but like divide this one by 4. So here you can see it is around 4,000, yeah, 4,600, and then width is around 2,000. So and then they do further downsample it by 16, and then the width and height reduces. So you are free to use whichever resolution you want, and the higher resolution you use, the more details you will be getting. So this dimension will print out the dimension of this particular one. So here -1 means the last resolution, and then 0 means the first resolution. So here you can get it, and then here I'm just going to plot the image. So this is this is the image of the last, like the lowest resolution, like 16, 1 divided by 16th resolution of it. So this is how the image is looking like. So why we need to do this is like, you can actually see this whole image tells you one information, but if you look in a smaller region, this image might carry more information, which is very important in order to diagnose, and in order to rate, in order to actually grade the disease. So analyzing it by patch is going to be playing a key role in this particular competition. You can't just analyze the entire image. You have to look into the patches, and interesting patches is going to be the key. So this open slide is going to play a good role in extracting regions from the interesting regions from the slide. So how do you do that is like, they have given us a model. So read region. So here you can find it, read region. So you're going to pass the location. So this will be the x and y coordinate, and then the level. So obviously which level of resolution you want, and the size. So how what is the, this will be the patch size of it. So here if I go, I'm just going to select a random point. So random width and random height. Actually this one should be height, and then I'm going to get a 256, 256 patch out of it. So since this is random, we can see the white patches apparently. So I'll just run this one until we see some useful image. So here we go. Some random patch is being extracted out, and this is how it looks. So this is the tissue of it. So you can see a much more detail. So here compared to this one, which is like, we're not able to understand much. This one has a lot more information. Like this is like putting it under your microscope, and you're observing more closer. So this will tell more information about it. So apparently it looks like selecting points out of random is not the good strategy to go with, because like most of the places are white. Even though we know how to trim it, but it's not going to be removing all the white spaces. We have to come up with a better process rather than the random to select the patches, and that's going to be the key for this competition. So with this, I'll just conclude it here now, and we'll just in the next video we'll start with building a basic CNN based model using TensorFlow, and we'll see how it goes on there. So yeah, thank you for watching this video. Yeah, bye.